point a telescope at a star, take photos and say, oh, there's an Earth-like planet at 1 astronomical unit.
Hi everyone, and thank you for joining us for today's episode of Becoming Multiplanetary. I'm one of your co-hosts, Rich LB, and my co-host today is going to be...
Hi, I'm Astrorody, host of STEM Study.
And today we're going to be talking with Ryan MacDonald, who is a postdoctoral research associate at Cornell University and is also a TSN Patreon. He has co-authored several papers on the subject of exoplanet atmospheres since 2015 and is here to talk to us about them. Ryan, how are you this fine evening?
I'm doing very well, and I'm really excited to be here chatting to Total Space, and can't wait to see all of the exciting questions that we have about exoplanets and these exotic worlds beyond our solar system.
Awesome. Well, we do actually have an audience link out to our Discord server as well, so we might even see some questions pop up in chat from time to time. So I will be keeping an eye on those as we go throughout the session today. So, Ryan, what exactly defines an exoplanet?
Sure. So the term exoplanet, it's a shortened version of the term extrasolar planet, which just means a planet orbiting a star that is not the sun. So if you imagine any of the stars that you see in the nighttime sky, many of them will have planets of their own, and any of those planets orbiting another star is an exoplanet.
And we know that there's been quite a few exoplanets already discovered since we've started looking for them. Do we know exactly how many of them have been discovered so far?
We do indeed, and the best resource to see the current count, there are a number of archives, but the most reliable one is probably the NASA Exoplanet Archive. If you just Google that, the current count as of today is 4,434 planets have been discovered. But these are just the confirmed planets. We have a couple thousand other candidate planets. Normally, we have to discover a planet by 2 distinct methods before we say that it's actually confirmed.
And speaking of, you were saying about you need 2 different ways to discover this. What kind of detection methods do you use for detecting such exoplanets?
Well, there's quite a lot of techniques that are used these days. Historically, the first planet which was confirmed was found actually a system of planets orbiting a pulsar, which is it's a very precise technique. It relies on very precisely timing the frequency of pulses that arrive from a pulsar, which is it's a neutron star, the core of a dead star that is rapidly spinning. And because of that, it has a magnetic field and it kind of beams pulses of radio emission towards the Earth. But if you have planets that orbit the pulsar, they cause the pulsar to wobble slightly due to the gravitational influence of the planet. And that produces a very slight change in the time that we receive the radio signal from at the Earth. And so that was how the very first planet that was confirmed was discovered. But that technique, there aren't actually that many planets around pulsars, so we haven't found many via that technique since. The first widespread technique is called the radial velocity method. So the idea here, it uses an effect called the Doppler effect. So if you've ever heard an ambulance drive past you, you hear the frequency or the pitch increase when it's coming towards you and decrease when it goes away from you. A similar thing happens with light when an object emitting light is traveling away from you or towards you. So it's a similar scenario. We have a star, we have a planet, the planet orbits around the star, but the gravitational pull of the planet on the star causes the star to also wobble slightly. It executes its own orbit. So when the star is traveling away from us, the light from the star appears to be slightly redder. We call it redshift. And when it's traveling towards us, it becomes bluer. And by measuring how much light from the star becomes redder and bluer throughout its orbit, we can actually not just tell that a planet is there, but weigh how heavy the planet is. A planet with a stronger gravitational field causes the star to wobble more, and hence the light red shifts and blue shifts more. So this was the technique that led to many of the early surprises, if you will, in exoplanets. So in 1995, we were completely surprised by the discovery of a giant planet about the size of Jupiter, orbiting 10 times closer than Mercury around a sun-like star. This is unlike anything we have in our own solar system. It was the first of a whole new class of objects that we call hot Jupiters, because we're not very creative at naming things in astronomy. And hot Jupiters, just by their very nature, just by the fact that they exist, rewrote many of our concepts of how planetary systems form. Because it had been imagined just from the solar system, where we have 4 rocky planets and then giant planets further out, that giant planets must form in the outer regions of a star system, while rocky planets must form from the leftover material in the inner disk. A hot Jupiter immediately showed us that something must be wrong with that paradigm, and led to the refinement of an idea called planetary migration, where giant planets form in the outer disk, and then either via friction from a disk that drags them inwards, or say another planet getting too close and they scatter each other, planets can migrate and end up really close to their star. So just from the very first exoplanet discoveries, we were being surprised. But if you then fast forward 10 years, the technique that is now the main technique that we use to find planets is called the transit method. And if you ever hear a story in the news about exoplanets, it's probably the most likely one that you'll hear. The idea is that you stare at a star for a very long time, and if a planet just happens to be aligned right that it passes in front of the star, some of the starlight is blocked by the planet, so we see a dip in the amount of light that the star emits. And the fraction of the star's light obscured by the planet tells us how large the planet is, its physical size. So the cool thing there is that if we can detect a planet via both the transit method to measure how large it is, and the radial velocity or Doppler method to measure how heavy the planet is, we can then work out the density of the planet from its mass divided by its volume, and hence we know if it's a rocky planet or a gas giant. And these are both indirect methods. We're not directly pointing at a star and seeing the planet here. We're indirectly looking at how the light from a star changes as a function of time to infer an unseen planet. So it's quite cool that you can tell that there is a rocky planet that you can't see just purely from looking at how a star's light changes over time. So the transit method is the most successful one to date that has found many thousands of planets, mainly from the Kepler Space Telescope that launched in 2009, and now from NASA's TESS mission, the Transiting Exoplanet Survey satellite.
And speaking of satellites like that, Joey, recently we've heard in the news that Hubble's payload, a backup payload computer recently is coming online.
I think everyone who's even just barely a fan of space and astronomy and things is going, thank goodness, because there were a few of us that were a little panicked.
Oh yeah.
Hubble has taught us so many things about the universe just by being able to look and get a clear image. So it's fantastic to see that coming back online.
Yeah, and we were waiting to hear back if we had got because Hubble Observing Time for a number of exoplanets. Like I was about once every year we get together amongst other astronomers, and we form teams, we write observing proposals, and when was it? I think it was March or April or so this year. I was on about 8 different teams where we submitted observing proposals for Hubble. So we were waiting to hear back if we had Hubble time. At the same time, we were seeing in the news about all the problems with Hubble and not even knowing if the telescope was going to survive. So it's a lot of time we put into just trying to get Hubble time as well, and then not even knowing if the telescope is going to be functioning was a real scare in our field, because so much of what we've learned about exoplanet atmospheres has come from Hubble.
If I recall correctly, wasn't the pictures of the pillars of creation also taken from the Hubble telescope?
Almost everything, any image you've seen from space, almost anything will be Hubble. Unless it's a very specialized thing like the cosmic microwave background. But yeah, Hubble, just phenomenal.
Yeah, it's astounding how much of a workhorse it's being. Like, even now, to this day, with the backup payload computer coming online, it's still going to be able to keep going. And yeah, it's being definitely used, that's for sure. So in terms of Hubble, Hubble operates in UV to visible light and near infrared. However, we have a new telescope, hopefully launching very soon, fingers crossed, the James Webb Space Telescope, which is mostly going to be into the infrared. Now, exactly what differences are there between infrared and ultraviolet spectroscopy? Like, what do you see mostly in one and what do you see mostly in the other? What are the differences between the two?
Sure, that's a great question. I should perhaps preface this a little bit with like how we can use spectroscopy to learn about exoplanet atmospheres, and then we can get into the specific wavelength ranges. So the main technique that I use for my research, one of many used in exoplanets, is called transmission spectroscopy. The idea is we observe a transit, just like I described a moment ago, to detect a planet. But when the planet passes in front of the star, you observe the transit in multiple different wavelengths. So if you happen to observe at a wavelength or color of light where the atmosphere is opaque, because there's something in the atmosphere absorbing that particular wavelength, the planet appears slightly larger. It blocks out a little bit more of the light from its star. If you observe another wavelength where the atmosphere is transparent, the planet appears to be a little bit smaller. So you can imagine sweeping through in wavelength and looking at how the size of the planet changes with wavelength. And this is what we call a transmission spectrum. And since we know from laboratory experiments on the Earth and theoretical quantum mechanics exactly at which wavelengths each atom or molecule absorbs light, we can use this to back out the composition of the atmosphere of the planet. So a planet that we are not even seeing directly, we can make a statement like, oh, the atmosphere of that planet is 1% water, for example, which is it's quite cool that we can do this. So in terms of what the different wavelength ranges tell us, in the ultraviolet, you tend to probe really high altitudes in the atmosphere. So that can then tell you about, is the atmosphere of the planet escaping? Because some of these planets are really close to their star, so some of the atmosphere is blown away. And you can see almost like a cometary tail around some of these planets. So the UV tends to probe right the upper atmosphere and can tell us about ions in the upper atmosphere, for example. And this is exactly the same as used in the solar system. So the upper atmosphere of Mars, for example, is routinely studied in the ultraviolet. In visible wavelengths of light that we see with our own eyes, you can probe, we call it scattering processes. So if you ever look at the sky and see that the sky is blue, unfortunately it's a bit cloudy over here today, but the reason the sky is blue is a phenomenon called Rayleigh scattering. So short wavelengths of visible light, which are more energetic, have a greater probability of being absorbed and re-emitted, so they scatter and bounce all over the sky, and that floods all the angles that we see on the surface with blue light, while lower energy light, like red light, tends to scatter less often and goes kind of in straight lines through the atmosphere. So in exoplanet atmospheres, in the visible, by observing, we call them scattering slopes, so how the scattering of the atmosphere changes with wavelength, we can not only figure out what the color of the sky would be on different planets, but if you have, we call them hazers, like small little particles in the atmosphere, like we see on Titan, for example, that produce that kind of smoggy yellowish color, we can actually infer the existence of tiny particles being lofted into the upper atmospheres of these planets in the visible. And since many of the planets we observe at the moment are hot gas giants at thousands of degrees, it turns out that at those temperatures, the gases sodium and potassium actually exist as gases floating through the atmosphere. And if you've ever seen a sodium or potassium street light, like those characteristically kind of yellow lights that they used to be used like all the time in the UK when I was growing up. I think they've changed some of them now.
Hi there, guys. It's another Space Nut here. Sorry to interrupt this show, but if you enjoy what you're seeing, consider supporting us on Patreon at patreon.com/totalspace. I'll let you guys get back to the show.
Yeah, they've replaced them with LEDs now, but I remember the ones you talk about, the old orangey yellow lights, yeah.
Yeah, so the same color of light that sodium gas emits at when you heat it up is the same color that it absorbs light at when light goes through it. So if you look at a planet and see it suddenly becomes a lot larger at that very precise color, kind of in the that orangey color, we know that there's sodium in the atmosphere. And that was actually the first gas that we ever detected in an exoplanet atmosphere in 2002. And that was Hubble that gave us that. So the visible tells us about scattering and about atoms like sodium and potassium. But when you push out to the infrared, that's when you start learning about molecules in the atmosphere. So visible light is very high energy. It can cause an electron to kind of jump between two orbitals, or orbits, if you will, depending on your knowledge of quantum mechanics, in atoms like sodium. Molecules can actually be excited, and I love this is the actual terminology that's used. If a molecule absorbs infrared light, it can kind of vibrate about its covalent bonds, or also kind of like rotate about those bonds. And it takes a lot less energy to cause a molecule to start vibrating than it does to cause an electron to jump between energy levels. So molecules have this whole forest of absorption features in the infrared. And each molecule has a very distinctive fingerprint because of the different atoms, the different numbers of electrons. Every molecule is completely unique. And so we know the signatures of each molecule very well. So the infrared, where James Webb is going to observe, will be an absolute treasure trove to reveal molecules that we haven't been able to probe with Hubble, because Hubble can only see a very limited range of the infrared. That is enough to detect water, though. We've seen water, although it would be in the form of steam, for these hot giant planets, for at least 10 planets, probably more like 20 now. But what we'd really want to do is see molecules like carbon dioxide, especially in rocky planet atmospheres, because that could tell us a little bit about the temperature of the planet. We want to see methane, we want to see ozone, potential biosignature gases. We want to see the building blocks of life, ammonia, hydrogen cyanide. There are so many molecules that James Webb will finally open this window for us to be able to see.
Fantastic. It's very exciting.
It is indeed. And next I'd like to talk, just before we go into your white dwarf opportunity paper, we talk a little bit about the Nancy Grace Roman telescope and how it is going to advance works within your field.
Absolutely. So the vast majority of planets that we've found and characterized to date is via the transit method. And I alluded to how difficult it is to just directly point a telescope at a star and take a photograph and say, oh, this planet's there, like you would do with a telescope to look at, say, Jupiter or Saturn on the Earth. It's hard, but not impossible. So with current technology that we have, we can use devices called a coronagraph to block out the light from a star, and by using fancy algorithms, extract the tiny patches of light that have either reflected off a planet, or in the case of really young hot planets, their thermal emission. So for planets that are about as far out as maybe Saturn, and they're very young baby planets, like 100 million years old, so they're shining in the infrared, their star only outshines them by about a factor of 1,000,000. Current technology can cancel out that factor of 1,000,000 using large ground-based telescopes, like the Gemini Planet Finder would be one of those. So we can see giant planets that are far out with current technology. Nancy Grace Roman is going to be a space-based telescope that will also directly image planet systems like this. And its target will be to detect and observe planets that are just like our own Jupiter and Saturn. So cold giant planets around nearby sun-like stars. Because these are really hard to find via our current techniques. They're so far out that they're very unlikely to transit. And if they did, you'd be waiting years and years for each transit event to happen. So it's hard to find them. We have found a couple, but just like one or two instead of thousands. So Nancy Grace Roman will obtain spectra of analogues to our own Jupiter and Saturn, but maybe a little bit warmer. So imagine if Jupiter was about 50 degrees hotter, for example. Those are some of the planets that we're going to study with the Nancy Grace Roman telescope. And so one of the things we're excited about doing will be trying to observe signatures of water vapor in the atmospheres of these planets. And the reason why this is interesting is that it's really hard to know how much water there is for Jupiter, Saturn, Uranus, and Neptune, because it condenses in the form of clouds. The planets are so cold that there are these thick clouds of water that are so deep that they're at depths 5 times the pressure of the Earth's atmosphere. And they're covered up by ammonia clouds and things on top. So the Juno mission is doing that right now using a special microwave instrument to probe down to that water layer. But it's actually much easier to measure water in the atmospheres of exoplanets than it is in our own solar system because of how hidden that water vapor is. And if you know how much water there is, you can tell something about how the planet formed. Because when a planet forms and they accrete loads of icy comets and material, and water is the most common ice that we have. So by measuring how much water there is in the atmosphere today compared to how much there just is in the sun, you can tell how much material fell onto the planet while it was forming, and hence where in the planetary system it originally formed. So the water tells us a lot about the past history of a planet. So yeah, we're hoping that by observing giant planets with the Nancy Grace Roman telescope that are a little bit warmer than Jupiter, just that tiny increase in temperature makes the water clouds evaporate, and hence you can get water vapor at much higher altitudes, and hence we can detect it. But ultimately, Nancy Grace Roman will be a technology pathfinder. What we really want to do in the long term is directly image Earth-like planets around other stars. Point a telescope at a star, take photos and say, oh, there's an Earth-like planet at 1 astronomical unit, and actually see a photograph of a pale blue dot around another planet. And that would not have to rely on the planet aligning just right for transits. You would be able to point at any star and be able to do this. We can't do this quite yet because the Earth reflects about 10 billion times less light than the sun puts out. So it's a little bit beyond our current technology. We can do about 1 million or 10 million, but not 10 billion at the moment. So Nancy Grace Roman will be a technology pathfinder to figure out how a future space-based telescope like the proposed LUVOIR would be able to use instruments in the 2030s to be able to directly image Earth-like planets around other stars. So it's studying gas giants, obviously for their own interest, but it's also a key pathfinder towards rocky planets in the decades to come.
Wasn't that just awesome? It was so exciting to speak with Ryan about this. If you enjoyed what you saw here, just wait until the second half of this interview drops. It is out of this world. Until then, why not check out these other videos from our channel that YouTube thinks you may like?